we shall see gate 2020. So this is gate 2020 set 2, question number 51. The question goes like, the water flows through a tube 3 cm internal diameter and length 20 mm. Outside surface of the tube is heated electrically so that it is subjected to a uniform heat flux circumferentially and axially. The mean inlet and exit temperature of the water are 10 degrees Celsius and 70 degrees Celsius respectively. The mass flow rate of the water is 720 kg per hour. Disregard the thermal resistance of the tube wall. Internal heat transfer coefficient is 1697 watt per meter square Kelvin. Take specific heat Cp of water and inner surface temperature of the exit section of the tube is. So first let us draw a tube to get an idea of about what's going on actually. So here is our tube. Okay, so they've also said that outside surface of the tube is heated electrically so that it is subjected to a uniform heat flux. So it is heated electrically, which means that some kind of wire setup is being carried over this. Okay, assume that it is spread over all the length. Okay, so keep that in mind. So they have said that, and the remaining things to be drawn is that mean inlet and exit temperature of the water. So water is flowing, so let me use a different color. So water is flowing as such. Okay, so water is flowing. So flowing water actually while going in is actually 10 degrees Celsius, while moving out is it's actually 70 degrees Celsius. Mass flow rate of the water, so mass flow rate is 720 kg per hour. Disregard the thermal resistance of the tube wall. Internal heat transfer coefficient, so internal heat transfer, so internal between the tube and the water, H is gonna be 1697 watt per meter square Kelvin. Specific heat Cp is equal to 4.179, quite a bit different, so have to have a watch over here. Inner surface temperature. Okay, so the data is given, del T is given, and also Cp is given, mass flow rate is given. So we shall calculate, since they are asking inner surface temperature at the exit section, we need to know the flux created by this outside of electrically heater, right? Electrical heater. So what we could do is we can just start with applying the energy balance equation. So this energy balance equation could be written as, so heat flux, okay, which is like Q by A into area, okay, area of heat transfer which is happening, okay, the cross sectional area as well as the the circumference and into the length. So should be equal to mass flow rate into Cp into del T. So from this we have got almost all the datas. So this energy balance, this heat flux into area will give you the Q. So this is Q, the total term is actually Q. Okay, so that is totally related to the water heating. Okay, that is the reason the water gets heated, okay, from 10 to 70. So that's what we have been calculating here. So now if you could see heat flux, we don't know, let me have it like this, into area is actually nothing but pi dl, right? So pi dl should be equal to mass flow rate, which is 720 divided by 3600. Cp is, they have given us 4.179 kilojoule per kg Kelvin. So 4.179, so 4179 into del T. Del T is nothing but 70 minus 10. Okay, so now we have only one unknown, and we have almost all the data. D is given, L is given, so just substitute. Okay, I'll just substitute once more and then I will proceed ahead with the answer. So into 60 divided by 3600 into pi into what is the diameter they have given, 3 centimeter and length 20 meters. So length is 20, diameter is 3 centimeter divided by 100, that I will put it on the top. Okay, so I hope you can solve this really easy. So just by using calculator you can solve this. So heat flux, finally you will get it as 26604.34. okay, so this is heat flux. So the heat flux unit would be around watt per meter square or kilojoule per meter square, depending upon the conditions. So right now we have used mass flow rate, so it's gonna be watt per meter square. Okay, so next is applying, we have got this heat flux obviously, so applying Newton's law at the exit. So Newton's law, convective heat transfer, applying Newton's law, you will get, so heat flux, so you all know that Q equal to HA, like del T or TW minus T infinity is what Newton's law of cooling. Okay, so now this A goes to this and it will become a heat flux. So now so Q by A would be 26604.34. what is H? H is gonna be 1697. So TW minus T infinity. So what is the T wall? So what is required, right? Exit wall. Okay, tube temperature at the exit wall, TW. T infinity is nothing but the water which is inside the tube. Okay, so let's assume that, so this is T wall and these are T infinities, right? So which is away from it, right? So TW minus T infinity, which is the temperature of the water, which is 70. So solving this, we have only one unknown, one equation. So finally you will get 26604.34 divided by 1697 should be equal to TW minus 70. So calculating this, you will get TW to be equal to 85.67 degrees Celsius. So temperature of the tube of the wall at the exit is actually, okay, right, temperature of the exit section of the tube is inner surface. Fine, so the answer we have got is 85.67 degrees Celsius. Key is between 85.1 to 86.1. So with this, well within the range. So this is our final answer. Thank you.